Hello, everyone. It's a great honor to have this opportunity to present our work on Amazon ESCI Challenge for Improving Product Search or KDP Cup 2022. Our team, Triple W, wins the first place in Tax 1, the query product ranking track. We are from Interactive Entertainment Group of NetEase Corporation, Guangzhou, China. My talk today will be in the following parts. The first is the text introduction and the data analysis. The second is the overall framework of our solution, which is divided into data preprocessing and the model architecture. And then we will introduce our basic model and training in detail. And finally, summary and feature work will be given. Okay, let me start with some general introduction about this competition. There are three tasks in this challenge. The goal of the task one is to rank the product list by relevance with a given query. The provided dataset contains more than 1.2 million products and 2 million query product pairs in three languages, which are English, Japanese, and Spanish. And the labels measuring relevance are of four categories, which are exact, substitute, complement, and irrelevant. How to better understand the semantic relations between query and product is the key to the task, and the final evaluation is based on NDCG. This is some of the basic data analysis. The label distribution and the language distribution are both imbalanced. More than 60% of the labels are exact, and more than half of the samples are English. The raw data is quite noisy, containing many useless HTML tags, symbols, and emojis. So we do some data cleaning work before training. Then we use Google API to translate all of the data into English, Spanish, and Japanese separately to do data augmentation. We also use tagged entity marker to incorporate the NER information into the input of the models. This is the overall framework of our solution. We use data sets of all three tasks to train the model. Then we do elaborative data cleaning, data augmentation, data translation, and incorporate the NER information as entity marker in preprocessing. As for model training, we use both multilingual and monolingual pre-trained language models as backbones, including LLMs, DBERT, and RAMBERT, to further boost the models. Adversary training with AWP and FGM self-distillation pseudo-labeling, multi-sample dropout, cross-attention, and prompt tuning are applied during training. Finally, we do model ensemble to get final summation. Our solution outperforms others both on public and private leaderboard for task 1. This is a single model, and the model architecture is shown in the figure. We use cross-encoder architecture based on DBERT, CHI-MS, and RAMBERT. For the downstream task, CIS embedding is used to do the ESCI for class classification. The query and the product information are concatenating before feeding into the models. We use softmax to calculate the probability of ESCI, and then use the cross-entropy loss as a loss function. Given that the data is labeled by cross-sourcing, it could be quite noisy for the model to extract the real information. To make the model more robust, we use self-distillation training to further boost our single model. The model itself is used as its own teacher to do distillation training. To be specific, we use threefold bagging training and make prediction on the auto-fold datasets to generate the soft labels for all of the training examples. And then we merge the soft labels and the ground true hard labels with weights 0.3 and 0.7 to get new training labels. On the other hand, we also use our trained model to generate a pseudo label from the public test set to do further training to avoid making the training data more noisy. Only samples from the public test set with predicted probabilities above 0.7 are used as pseudo labels. Adversary training significantly improves the resistance to adversary attacks for our model, thus improving model robustness. When the loss is below some threshold like 0.6, we start to use AWP in training steps that adversarially perturbs both model weights and the embeddings. Besides, we also tried FGM, which performs slightly worse than AWP does on the public leaderboard. Dropout is an efficient way of avoiding overfitting during training. In our experiments, we use a group of dropout layers with dropout ratios between 0.1 and 0.5 to make our model more robust. Besides, features from different layers have different representations. As a result, fine-tuning the model with different learning rates can make it more robust. Due to the multi-layer structure of transformers, different layers capture different levels of representations. The output of the last layer may not always be the best representation of the inputs, so that weighted multi-layer pooling was used to get the final representation from different hidden layer outputs. At last, our model ensemble is used to achieve the final boosting. We use different model backbones with different settings, as mentioned above, to improve the gain of the ensemble. And the model ensemble weights are mainly determined by the public scores and also the local cross-validation scores. We also lower the weights of the models with high correlation coefficients. Our score is improved from 0.9022 to 0.9057 on the public leaderboard, and from 0.9015 to 0.9043 on the private leaderboard after ensemble. These are some of our major summations results. The scores of our single model without any pre-processing and post-processing are around 0.893 on the public leaderboard. After doing some data cleaning and hyperparameter tuning, our model is improved to 0.896. Self-distillation, pseudo-labeling, and label smoothing helps us further boost the model performance to 0.899 on the public leaderboard. With English pre-trained language models and adversary training, we can achieve 0.9022 on the public leaderboard and 0.9015 for the private. And this is our best single model. And last, we do model ensemble to get a final boost from 0.9022 to 0.9057 on the public leaderboard and from 0.9015 to 0.9043 on the private leaderboard. In this work, we propose a semantic alignment system for multilingual query-productive retrieval. We use multilingual and English pre-trained language models as backbone with a combination of data pre-processing and also training optimization. We are able to improve our score to 0.9043 on the private leaderboard with ensemble, which ensures us to win the first place. However, English and multilingual models are both used in our solution is kind of redundant for training and also inference. We believe it's possible to improve the English representation ability for the multilingual model by model distillation or further pre-training with more English corpora or something else. Obviously, end-to-end multilingual language model is much more concise and flexible to solve this task in a more elegant way. We are leaving it for future work. Okay, that's all. Thank you for your attention, and we would like to thank everyone associated with organizing and sponsoring the KDD Cup 2022.